Okay. Well, thanks a lot. It's really a great pleasure to be here. So I'll be telling you about a recent paper that I did with there's Enrico Herman, there's Radu sitting right there, Mikkel Roof, and Mao Zheng. Um, so the problem I want to talk about, it has applications at high loop orders where the fact that there's no natural definition for an integrand causes great grief. And the basic problem is actually pretty simple. Let's say I draw, here's a planar integral, and I choose some kind of labels. Maybe let me pick L1 and L2 for the loop momenta, and then let me pick a non-planar integral. And, well, I'm not really sure what I'm supposed to do if I want to somehow correlate this. I could pick, I guess I could try to pick some labels that look similar. But of course, because the integrals are non-planar, there's no way that you can really make a choice that's canonical or natural or anything like that. If you're only focused on planar integrals, I'll make some choice, I don't know. I'll label this one L1 and this one L2. But if you're focused only on planar integrals, then there is such a choice. It's the dual variables of dual conformal variance, and you can use that and define some kind of a global integrand and do all sorts of things with that. Now, I'm not going to solve this problem. Integrands. Yeah. Well, there is one, yes. The real problem is nobody has done what you said, despite years of trying. So, of course, all of us, we have all sorts of ideas, and there's all sorts of tricks you can think of like having infinitely many labels and all the possible relabelings, and then that way you try to define some kind of a global integrand. But all attempts have either failed or have been useless, one of the two. So we're not going to solve that problem. So we are still going to not know how to label these things. We will make arbitrary choices on labels, but we will do something pretty good, which is define a basis, an integrand basis. And once you're in a basis, you got most of what you want, because you can then use it for all sorts of problems. For example, the obvious one is in a basis, the coefficients are unique, right? Because you have a span, like a vector space, and you span the space, and as long as it's not overcomplete, every coefficient is unique. And in that sense, you can define a unique integrand. Yeah, yeah. Yes. Yeah. Okay. Yes. 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 That's the general. That's right. So maybe this is too simple. You can certainly at lower loops you can get away with things, but the place we want to apply these ideas is 4 or 5 loops. 5 is the place where we've been having serious trouble because of this problem. It's related to this problem, like see the double copy to all loop orders. So I'll show you how to solve that once you understand this idea of a basis. Okay, so the idea is focus on a basis. So it has to be a basis, and then you can do many things with that. Okay? And so just maybe to just say a couple words about where we're going. So the first thing is the idea of unique integrands. Okay. Now, okay, the integrands actually won't be unique, but in the basis they're going to be unique, right? So the coefficients are going to be unique. Once you make a choice, there'll be a set of choices we make. Once you make those choices, then no matter how you calculate the integrand, maybe for whatever reason you like light cone gauge, somebody likes Unitarity method, someone is an old timer, an old guy like me, they want to do Feynman diagrams and Feynman gauge, and no matter how you do it, it'll be the same answer, the same integrand. Okay? That's what this construction will do. And the other thing it'll do, like there it is, generalized unitarity, it'll greatly simplify multi-loop unitarity. Now the way it does that is not very profound. If I have a basis, then I can look at one element in the basis at a time. Let's say I'm using unitarity and I'm trying to match a unitarity cut to an integrand. I pick one term and I match it to the same term in the integrand. One term in unitarity on the unitarity cut will be one term in the integrand because I'll be working in a basis. And that greatly simplifies, let's say we're trying to do gravity at 4 loops or supergravity at 5 loops, where things get pretty complicated. You really want a basis. So you're just doing one piece at a time, and it's not entangled in some complicated way with other things. And maybe you have to solve large linear systems, which is the way we would have done things a year ago, but now we're never going to do that. We're always going to do work in the basis, one term at a time, to do unitarity, generalized unitarity for integrand construction. And what flows out of that is kind of a trivial solution to the grief we've been having to get the color kinematics duality and the double copy to work at high loop orders, like at 5 loops. There's grief up there. And the way we solve the problem is kind of trivial, because once you simplify multi-loop unitarity, then you can do double copy on the cuts, because if you use cuts that are built from trees, double copy always works on trees, so therefore you can immediately solve the problem to any loop order. You have a method now for doing double copy at any loop order, and it's an efficient method. Okay? So the reason why I'm talking about these applications is you're going to find out that, in fact, the solution to the problem is kind of trivial. It's not very profound. What is profound, or I hope you find profound in this talk, is not the way it's solved. That I think you'll find to be not very complicated, but what you can do with it, right? The applications. And we're not the first people to talk about bases of integrands. These ideas, all the ideas I'm going to talk about, some version of them has appeared in the literature, bits and pieces. Okay, but of course you have to assemble it into a coherent framework in order to apply it to these multi-loop calculations. Okay? Yeah. Oh, there's a question, sorry. No. D. Yeah, well, we like arbitrary dimension because in some way it's logically simpler, because if you're working in 4 dimensions, you have constraints like Graham determining constraints, and they're nonlinear constraints. And then you can get all sorts of relations between, let's say, a hexagon diagram and box diagrams at one loop. And you can apply all that. You can do that. You can put that on top of what I'm talking about. But here we're working in D dimensions. And there's another reason we want to work in D dimensions. It's because when you're doing multi-loop calculations, let's say for the gravitational wave problem, you do have to work in dim reg. So once you're in dim reg, then you might as well be thinking about it from D dimensions. Yeah. And there have been, anyway, these ideas, let's say the idea of a basis, we're not the first. You can find, there's prescriptive unitarity. I'm not going to explain exactly what that is, but anyway, it's a cool way to diagonalize. Oops. It's a cool way to diagonalize the unitarity cuts, and it's been applied to all sorts of problems with large numbers of legs. We've got 2 authors here. Oh, one of them is playing hooky. But anyway, there's Yaroslav. Yeah, Jake, and there's, I got the list. There was Jake, there was Enrico, there was Langer. Somehow you, but I guess it was a later paper. But anyway, you apply prescriptive unitarity. Okay. And then I'll be talking a lot about, I'll talk about inverse propagator, inverse propagator basis. Basis for Lorentz, for invariance, like dot products. Okay, if you look at any paper, there must be thousands of papers who use this inverse propagator basis, because when you're doing integrals, the integration by parts, this is exactly the basis. Inverse propagator basis. You take the dot products and you write them in terms of inverse propagators. Anyway, we adopted here in what I'll be talking about. We'll be using that. That'll also be very important. Okay. No, the color just goes along for the ride. I mean, you have to always be in a basis. So let's say you have color, you better squeeze out all those Jacobi identities. Otherwise, things may not cancel, or things might be ambiguous. So you have to, if you have something like color, you have to force yourself into a basis. You always have to be in a basis for any extraneous things, like color or polarization vectors. Everything has to go into a basis. A basis. Go to a basis. You have to go to a color basis. Everything has to be in a basis, or things don't work right. Anyway, we're mostly going to work on gravity, so at least there we don't have to worry about the color. Okay. So the procedure. Let me actually just tell you how to do it. So procedure. Okay. Step 1. Is what you want to do is identify top-level graphs. Top-level graphs. Oh, so another thing is we're going to be doing things diagram-oriented. So everything will be in terms of sets of diagrams that look like Feynman diagrams, but of course they don't have to come from Feynman diagrams. It's just a way of categorizing integrals. And the reason why we do that, there's actually a very practical reason, is if you want to ever take one of these integrands and integrate it, you better be in a diagrammatic format so you can use all the computer programs that allow you to do these integrals. Otherwise, you're in trouble. But in any case, this is how we organize things. This is the way usually the double copy is organized. But I'm sure there's much fancier things to be done. Okay, so by top-level graph, let's just pick our favorite simple example. So this is the top-level graph. That's a top-level graph for the two-loop 4-point. This you might be tempted to call this thing a top-level graph, but we don't want to do that. So we're defining the top-level graphs as the ones with the maximum number of propagators that carry loop momentum. So this one, in this basis, I won't count this as a top-level graph, even though it has maximum number of propagators, but this doesn't carry loop momentum. Let me just write it as 1 over P1 plus P2 square, and then one of these. And this guy we'll call, could be a daughter graph. This is a daughter graph. Okay. Okay, and then what we have to do is find all the daughter graphs. So step 2. This is to build the basis. Find all the daughter graphs. Okay. So as a trivial example, what you do is you just, let's say you start with this thing. Maybe I have another color. Probably don't have any other color. Okay, so I just start crossing out propagators. Let's start with this one. As I cross that out, I get this graph. Then I do it again. Maybe I get rid of this thing. I do it again. Okay. So, and I do it in all possible ways. Oh, then let's get to the last guy. Then over here, I could get to a guy, let's say I pinch one more, I cross out this one. I'm going to cross out this one, and then I get to this one. Oop, like this. This thing, I dropped. Let's just ignore him for a while. Okay, so don't do this. Forget that. That's an unhappy graph. It has a tadpole. So drop tadpoles and bubble on external leg. We'll see in a second why you need to do this. And do it in all possible ways. All possible ways. Yes? Yes? Yes. You mean the supergravity or the? Yeah, there's. Yeah. Okay. So yeah. So this procedure, I mean, this procedure does cause lack of, I don't know what's the right word, canonical power counting. But the good news, for the types of problems we're interested in, let's say it's 5 loops, there is no better way than this. I mean, even if you're messing around with a power count, like you're making it worse. Yeah, it's not ideal, but it's definitely no worse than any other idea we've had. So it's okay. Yeah. Yeah. So you don't want a graph like this, for example. You would not consider this a top level. You just get rid of the middle guy. Yeah, just one PI. Right. No. I mean, it could be. There could be this one. No. Top level. Sorry, this is not. Oh, sorry. This is not. By our definition, this is not. Yeah. No. This I would call a daughter. Yeah, I would call it. I would call it a daughter because it can be derived from, say, this one by pinching. So once I have the top level defined in some theory, like in gravity or in gauge theory, we're interested in 3-valent. Maybe some other theory, we're interested in 4-valent. But anyway, it's the graphs with the maximum number of propagators that carry loop momentum, and then yes, absolutely. In other theories, it could be four valence. Yeah, 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 right. I mean, you certainly want to adjust the basis according to the theory you're looking at. Okay. Yes, I should tell you about these, what I did here, because some of you may start complaining very loudly, because I'm talking about a basis, and there's a piece of the integrand that I'm ignoring. So actually, let's look at, why in the world I'm dropping this. So let's pick this diagram. I'll make it two loops. Okay, this is a very unhappy diagram because that's on shell, that's on shell. So this is 1/0. Okay. So that's not so happy. Now, in a massless theory, what we can do is mumble very quickly, scaleless integral, that's a scaleless integral, therefore this integrates to 0, so don't worry about it, it's just going to be 0. It'll be like 0/0, but it'll actually be 0 because it's a scaleless integral. Dimensional regularization will throw it away. And in fact, you can do that. There's a little bit of chaos because it mixes infrared and ultraviolet singularities. But if you know the infrared singularities and you know the ultraviolet singularities, which we do know for the theories we're interested in, then it's really not a big deal. So if it's massless, we can just replace crossing this out with another rule which says drop scaleless integrals. Or drop anything in the integrand that leads to a scaleless integral. Just throw it away. Okay, and that's the end of that problem. But you may say, okay, what about a massive theory? Now you can't do that. And then you're going to say, but then you don't have a basis because you haven't included these things that you actually need to include in the theory. And the answer to that is drop it anyway. And the reason why you want to drop it is because no matter how you twist and turn, this thing is ill-defined in the integrand. So you do not want to define this thing in the integrand. Now, you may notice something else, that as you're marching down here, you see this is all well-defined. This thing feeds into this, feeds into this, feeds into this, feeds into the thing that's ill-defined. Right, the scaleless integrals, or these like bubble on external leg things. You don't want any, no tadpole, right. Yeah, no tadpoles, tadpoles are forbidden. Yeah, we don't want any of this because it mixes. See, the 1/0 is evil because it contaminates, right? Absolutely, I should have been clear about that. I don't want this and I don't want that. And the reason why I don't want that is this is ill-defined, and once this thing is ill-defined, there's a piece under it which looks like that, and then my confusion here contaminates my confusion there. So the solution is throw it all away. So then you say, but you don't have the integrand. Oh, but we do have the integrand. We have the integrand for all terms which are not evil. So then you say, but you still have a problem because you're missing a piece. Well, don't worry about that. What you do to solve that problem is you don't consider this issue. This issue, you delay it until after you've done the integrals. And the reason why you can delay it, if you remember in gauge theory, when you do that integral, let's say this is an off-shell green function. Suppose let's throw it off-shell. So everything is well defined. What happens is this propagator cancels, right? Because that bubble is proportional to that propagator. So there's no singularity in the, if you take the green function and you integrate it, then this thing is gone. That singularity, the 1/0 is gone. It's not there. Okay, and So the idea, which I will not explain in any detail, but I'll point you to an example. Right. So the rule is ignore tadpoles and bubble on external leg. Leg until after integration. Okay, that's the rule. And then after integration, you say, I'm missing a set of functions, right? I have the amplitude. I have the integrated amplitude. I do all the integrals for all these pieces. I have the integrated amplitude, but I have certain errors. And the errors are that I didn't include all of this. So then what I do is I patch it because I know the functions that are missing. And the way you can patch it, well, I don't have a proof that this works in all cases, but if you want to look at a nice example, there's me, Cosmopolis, and Zhibadev. It's a gravity case. The basic idea is that you use the knowledge of the infrared singularities, the ultraviolet singularities. You can do this in multiple dimensions, or use knowledge of what those singularities should look like to fill out the missing functions, because it's a finite set of functions that are missing. And you just have to figure out the coefficients. So you do it by matching to known infrared and ultraviolet. That's the basic idea. You can also use other information. Again, other information is if you have a massive theory and you take m goes to infinity, it's supposed to have a good low energy effective field theory. And you can use that information to also determine this. But anyway, let's just ignore it. Let's make believe we're working in the massless case. So it's a problem that, anyway, the key is this problem, you want to delay it until after integration. Because after integration, there's no 1 over 0, because this, if you do that integral, it cancels out propagator. So there's no 1 over 0. And then you can use other information to figure out the missing pieces. Okay? Yeah. Yeah, maybe I cancel it. Maybe there's something in the numerator that cancels this propagator. Or at the moment, all I'm really doing is just classifying graphs. To define the basis, I need a collection of graphs. And what's the set of all graphs? I start with the top level and I start crossing out. And then I throw away these tadpoles, and that gives me the collection of graphs. And it's that collection of graphs that will be used to define the basis. No, we don't use, at least in this room, we don't use Feynman rules. But yeah, it can come. Well, the amplitude can come from anywhere. So somewhere, late at night when no one is looking, you use Feynman rules. You calculate an amplitude, and that amplitude is written in terms of diagrams. What we have to do is rearrange those Feynman amplitudes written in terms of the Feynman diagrams. We have to rearrange it in a certain way according to this basis. That'll be the idea. Yeah. Excuse me? Okay, that's mathematics beyond me, but it's here. Just think of it pretty simply. You're just collecting all possible graphs you could have, and graphs that can come not just from the Feynman rules, but if the Feynman rule generated a numerator that happens to cancel a propagator, then you want to include it in this list. Yeah. Yes. That's the base. Well, it's basically because I hit this problem. Yeah. Yeah. Yeah, generally we don't use the single cuts. It's, I mean, there's endless grief with this. I mean, a basic problem is, there's no real cut here because this thing only depends, let's say it was a massive theory, it only depends on the mass. So that actually doesn't depend on the kinematic, there's like no physical cut in the kinematic space. So it causes endless grief and confusion. So the solution, the best solution I know is don't talk about it at the integrand level. Wait until after the integrals are done, and then try to fill out the missing pieces using other information. You notice how we keep on dodging things, all sorts of problems, like this 1 over 0. Say, no, we'll just dodge it. Just ignore it, and we'll deal with it in some other way. And also this thing about the labels, right? I'm not going to tell you how to label. So I'm just ignoring that problem and just, focusing on things that we can do and things that we find important for doing these multi-loop calculations. Okay. Okay. Yes. That's something very important. The daughters. Step 2. Find all daughter graphs. So there's something very important about that. Because, you see, now you have, maybe let's cross out this leg, and maybe let's cross out this leg, meaning I cancel it. This gives me a daughter, and the daughter looks like this, like this. Okay, there's my daughter. Whoops, yeah. No, actually, maybe better. Let me just cross out this leg. Okay, so I'll get a daughter that looks like this. Okay, so I'm going to cross out that leg, so it brings it over here. Let me cross out the same thing. I cross that out, and then you see this comes over here. And, this leg moves to that side, so it actually goes to the same place. But now you may notice something, that the labels are completely messed up. If I take the daughter and I follow the labels, right, I get L1, L2 labeled like I had here. But if I take the daughter from here, let's go over here, I get, I get the same graph, but of course the labels are different. Let's see, this one is now L1 and this one is now L2. But it's the same graph. Well, you don't want two graphs that are the same with different labels. So the solution, of course, is just relabel it. Pick one representative. So if I get it from here, let's see, there's a numerator that canceled this propagator. Right, and I get this graph, which happens to be the same as that graph. I just want to relabel it. And the rule is, for the basis, let's see where I can put this. I want to put it here. Pick one representative. Okay. Pick one representative. So, you see, if I have a daughter that looks like this with this label and a daughter with those labels, and these are supposed to cancel, they can't cancel unless you put them in the same label. So you put them in the same label. That's all you do. There can be many. Anyway, these daughters can come from many places. So always pick one representative. It doesn't matter, So you can make any choice you like. We don't specify that. Maybe there's some preference why you might like one over another, but just pick one. It doesn't matter which one, but only one. And if you happen to have graphs with automorphisms, maybe another thing is, while we're talking about one representative, so find all daughter graphs. Pick one representative graph, with one set of labels, and it's that guy will be in the basis. That graph with those labels will be in the basis. Yeah. Yes, indeed. Okay, that's step 3. Step 3 will explain how to do that. Absolutely, because in fact that process is ambiguous. Okay, so this is just selecting out daughters and how to label them. Okay. Pick one with one set of labels. Okay, and if you have, maybe just a little side thing, if you have some graph and it has some automorphism in it, you better knock out that automorphism, right? If something is labeled like L1, L2, L3, and then the graph is the same, then you just want to remove that automorphism, basically mod it out, so that terms only appear once. Every term that is in the amplitude needs to appear only once. If the term can appear twice, you haven't finished, right? You have to make it so every term is unique. If you didn't do that, you wouldn't have a basis. Okay. Okay, so then let's get to step 3. Step 3 is Yaroslav was hinting at there was something ambiguous about what I said. So you have to also choose a basis of Lorentz invariant products. Lorentz invariant products. So in any graph, usually we do this for the parent graphs, and daughters inherit whatever we decide to pick for the parent. So the parent, you have to pick a basis of Lorentz invariant products. And how many of them are there? So let's ignore polarization or spinors. Then there's pi dot lj. Okay, and these, there's maybe n of these, and there's L of those. Okay, so it's n times L of these. You can also have Li dot Lj, and there's L plus 1 divided by 2 of these, and you have to pick a basis. Now, what basis are you going to pick? Well, of all the bases you can pick, there's one that's very special, because it makes your life simple. Because, see, we're trying to map from parents to daughters. So if I happen to have a basis that makes obvious how that works, that life would be good. So the basis I want, the basis, is inverse propagators, and the rest, we pick some dot products. We'll call them irreducible scalar products. If you happen to come from the world of integration by parts, they're called ISPs. So inverse propagators and irreducible and these irreducible scalar products. The inverse propagators make a lot of sense because they give you the parent-daughter relation trivially. So let me just write down a little more clearly what I mean by that. So let's pick our favorite double box. So there's L. Let's make that L1. This is P1, P2, P3, P4. Right, so I count 1, 2, 3, 4, 5, 6, 7. So there's 7 inverse propagators, props. So for the dot products, we're going to pick, let's call this P1 capital P is L1 square, P2 is L1 minus P1 square, etc. And then all the way, anyway, I got 7 of them, P7, just corresponding to the, right? I just write them down, the inverse propagators. And then, let's say, I don't know, L2 plus P4, for example, square, 7 of them. And then I need 2 more. If you can count there, n times L for 4 and 2, and you do the arithmetic, you'll see you need 2 more. So the 2 more, you have to pick something that's independent of these. Usually the way you do that is you pick this loop momentum and this loop with an external momentum out there. So maybe let's call them ISP1 is equal to L1.P3, and then ISP2 is L2.P2. Now, of course, you're going to say, but you didn't respect diagram symmetry. Maybe you should have respected diagram symmetry. Yeah, maybe we should have, but you don't have to. Well, this thing moves you out of the basis. If I reflect, if I flip things, it moves out of the basis. So diagrams. So maybe one simple. Let's say this one, or see, under diagram symmetry, these inverse propagators move very nicely. This one moves to this one. This one moves. Let's say I flip it. Symmetry. No, symmetry. The diagram. Yeah. So this choice looks pretty random. It doesn't respect anything. And the answer is do as you like. It's free country. Pick what you want. Maybe some choices are better than others, but it doesn't really matter. You just have to pick something. Okay? And it's this basis. So this is now a basis within our basis. In a diagram, there's a basis of inner products. And this is the basis you want to pick. This is the happy basis. And the happy basis plays very nicely with unitarity, because a unitarity cut is simply one of these goes to 0, right? Or a bunch of these go to 0, right? These do nothing. They just hang around, right? This is a basis. And so unitarity can act very nicely on it. The parent-daughter relation is also very nice. To go from here to here, I don't know, let's label this thing P5. If there was a P5 in the numerator, this inverse propagator was in the numerator and it canceled out, I come here. So I can immediately read off, once I'm in this basis, I can read off who belongs to a parent and who belongs to a daughter, right? So if I have a parent, suppose I had a parent, let's make this P5. There's a parent, and the numerator, I don't know, let's see, it was ST plus, P5, P7 plus, et cetera. And I want to know where this belongs, this term, this term, I know where it belongs. In this parent, that's where it belongs. Where does this guy belong? It belongs in this daughter, just by reading off, right? Inverse propagator cancels the propagator, and then I take that and I assign it to this diagram. So terms are assigned to diagrams very easily. I just read it off, right? That's an advantage of this basis, and this is, in fact, exactly how, let's say, the integration by parts programs work, relating different integrals, how we categorize it. Okay. And this is something crucial, right? The way I can run into trouble, I don't have a basis, is if I took this term from a Feynman diagram and I say, well, it's a Feynman diagram, I need to leave it here. Right? That's bad. You don't want to do that. You need to move it into the daughter. And then if I find, let's see, I started with this diagram and it winds up in the daughter, I can also have a term, a very similar term, cancels that propagator, comes to this diagram, and I say, no, I need to put it in the unique place, right? So I put it here. Right, so the idea is, with this inverse propagator basis, terms are flowing into unique places. That's the key. Yeah, it's just basis, and the amplitude will be put into this basis. Once we have, so the amplitude is some collection of diagrams and numerators, and then I start sorting the pieces and putting them in the basis. So what happens? So what happens? Let's say I have this idea works for planar and non-planar. So let's maybe look here. So let's suppose I'm looking at a term like s times t. It doesn't involve s times t. So this s times t doesn't cancel any propagator. So the place I put it is in this diagram. Here I have a non-planar diagram, which will also be in the basis. And I have s times t, I just leave it here. On the other hand, if I had a term, like here it was p, which canceled the propagator, I go to the daughter, and this guy goes to the daughter, which I then map to this daughter. Right? So all planar and non-planar have a spray of daughters, and then I make sure that if I see a daughter that is identical to another daughter up to labels, I put them in the same place. That's how the basis is defined. Okay? And that's, in fact, step 4. Step 4 is exactly what I described. Step 4 is apply to all parents and daughters, this description that the parents and daughters, and then give it a name, and the name we give is the global basis. This is A, not the, because of course there's many bases. It depends on exactly how I define these ISPs. For example, it depends what labels I use. But anyway, a basis or an integrand, let's call it a global. By global, I mean planar, non-planar, everybody. A global integrand basis I guess, or let me say, this is a global integrand basis. Okay? This procedure. Right? And you notice I didn't do anything profound here. All I did, all we're doing is I see a term in this diagram, and it looks like a term in that diagram. Right? Once I cancel the propagator, I have to cancel the propagator so the propagator structure is the same. And then I just map them to the same place. And I collect everything. Right? And the claim is, if I do that, the integrand is unique. Integrand will be unique. In the basis. Yeah. 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 Yeah, the mix. Yeah. Once, yes. Yeah, well, you have to, yeah, you're choosing a set of ISPs in each integrand, and they're fixed. Now, if I change the ISPs, what happens is I can generate a new spray of daughters, right? Let's say I change the ISP, right? The difference between my old set of ISPs and new set of ISPs is going to be a bunch of inverse propagators. So the basis changes around. But never mind, pick one basis, and that basis you use throughout the calculation, you never change it. And if you fix that basis, meaning you choose these ISPs as you like, you know, as an independent, they have to be independent from the inverse propagators, then the integrand is unique. And the word unique only refers to the basis, right? So it's not really a unique integrand, but with those choices, it's now fixed. And the consequences of this is that, for example, gauge independence. I'm working, let's just pick some consequences, just to be very explicit. So once I have a basis, and then, for example, you know, my first year of quantum field theory, and the professor is torturing you and saying, in QED, go use different gauges and show the answer is the same. And the poor student now has to do all the integrals. But if the student were to read our paper, they would realize that integrands are unique. So for example, let's pick scalar electrodynamics. Let's just make it scalars. I'll say a few words about if you have external polarizations, what you're supposed to do, or external spinners. Right, and you decide for whatever reason that maybe, I guess you're a professor trying to torture students, you say, okay, here's my electrodynamics. D dot A square, and then plus the sum from I equals 1 to 2, d mu phi I dagger d mu phi I. I make it two different flavors, so I have fewer diagrams. Okay, so that's one flavor, another flavor. And this thing depends on the gauge, right? This is C dependent. And normally, there's only one way to check the gauge invariance, which is, you know, do every single integral. And I do you have to integrate everything. But anyway, in our paper, you can find all the gory details. You take this thing, and you put it into the base. You choose some basis, and you take every term. You put it in the basis, and, of course, this drops out. Drops out at the integrand level. Okay, which is kind of cool. And in fact, we have used it in one of our papers. This is it was electrodynamics, but it was for the purpose of trying to do what's called fifth post-Minkowskian order of gravity. So you pick electrodynamics. Now you got, of course, in electrodynamics, you're trying to understand, did you construct the integrand correctly? So, it's word identities made stupid. I think what it means is if you're a professor and you forgot to teach ward identities or Taylor Slavnov or any of that stuff, it wouldn't matter because you could then understand the gauge invariance of physical quantities. It's basically a statement that integrants of S matrix elements are gauge invariant, and this is how to manifest that. Okay, and normally we've always thought about it at the integrated level. Okay, so that's a 5. This is 4. Oops, I lost the loop. Sorry, one more. So this would be QED, and it works exactly as stated. for the simple case. So we've applied it to some complicated case. Did I forget something? Yeah. What? Yeah. Yeah. Exactly. Yes. Well, it's basically what it's saying is it's gauge invariant, ignoring those terms. So in this, the basis is now chosen, but then there's some terms you're not looking at because they have this annoyance of the 1 over 0. So as long as you don't look at those, this drops out. And the place, of course, that you would want to study this, is that stuff gauge invariant, is after you integrate, not before. Okay. Yeah, so they get a 95, not 100, but it's okay. But certainly the complete cleanup. Well, certainly you're going to find any mistake, like the gauge. You can check gauge invariant, but you're absolutely right. It's in a sense, it's not, because of that annoyance, bubble on external leg stuff. Oh, and of course in the massless theory, it is gauge invariant because all that integrates to 0. So it's only for the case of massive where there'd be some extra hassle to go deal with that. Okay. Actually, that's kind of fun, and you can prove all sorts of things, like in the for example, a ward identity. Let's consider maybe something like this, and you want to check an on-shell ward identity. You can also do this at the integrand level. But speaking of polarization vectors, so if you have amplitudes with polarization vectors, you have to extend what you mean by an ISP. So if you have a theory that has a polarization vector, there's epsilon I dot L, or epsilon I dot PJ, LJ. What you have to do is put this in a basis, right? Don't make this over complete, or you're going to be in trouble because then things won't work right. So you just put this in a basis, and you're good to go. And the same with spinors. Whatever expression you have, make sure that you've squeezed out Dirac equation and anything else that means you don't have a redundant. So for example, you better use this, right? So that you have a true basis. And as long as this is a basis, this thing should be treated the same way as the ISPs. They just go along for the ride in this organization. And if you want to check a ward identity, an on-shell ward identity, right, then epsilon I goes to pi, the thing is supposed to vanish. So you can do that at the integrand level. All you have to do is make that substitution, go to the basis, and you'll find term by term by term it's 0. You don't have to do any integrals. Okay. You can do the same thing for soft, like Adler zeros. You'll find that in our paper. Everything's integrand. Well, Slavnov-Taylor doesn't make much sense because all of that is off-shell. The only thing we have is the on-shell ward identity. Yeah, it's all, yeah. So these are the analogous thing to Taylor-Slavnov that you might want to check. And that's all works at the level of the integrand. Now, okay, I got to move. Okay, so yeah, so I want to talk about the double copy. Maybe I'll try to be quick about defining it. So the way we do multi-loop supergravity calculations, or or also the gravitational wave calculations, is through the use of the double copy. And let me just very quickly review what that is. So at tree level, what you do is you take the Yang-Mills amplitudes, you take gauge theory amplitudes, and you rewrite it as cubic, the sum of cubic diagrams. Okay. So this is this set of cubic diagrams, and you rewrite it that way. So if you had a 4-point interaction from let's say Feynman rules of Yang-Mills Feynman rules, what you do is you look inside here for a color factor, and if you see the same color factor, let's say there's a color factor, this has a color factor, this has a color factor. If they're the same, all you do is you multiply by, let's say, S12 divided by S12. You just put back the missing propagator. So you can take any contact term, blow it up into cubic diagrams. You make this organization. And these diagrams, well, this can be embedded somewhere. Let's call this one I, this one J, and this one K. And maybe I'll put some labels like A, B, C, D, A, D, B, B, C, and then one more time, C, D, B, A. Then these color factors, Ci plus Cj plus Ck equals 0, and that's the Jacobi identity. And the idea is that if you can find a representation of this amplitude such that you get the correct amplitude, and these numerators, Ni plus Nj plus Nk, and this is of a bigger diagram, so this is embedded in a bigger diagram. If you can find a representation such that the numerators satisfy it, then let me write down gauge. So this is gauge theory. Then what you find is that gravity, and this is Einstein gravity, is given by, let's call this M tree, and this is gravity, is given by the same formula with those same ends, except, oops, that's an I. Alpha I. Okay, these are the Feynman propagators. And I put a little tilde here because maybe this is some other theory. It could be the same theory, it could be another theory. If it's two Yang-Mills, if this is ordinary Yang-Mills, that's ordinary Yang-Mills. Then out here comes Einstein gravity. So this is very cool. Okay, and this has been proven. These days you can just download some Mathematica and it'll generate these things for you. So we know exactly what these ends are. Now, you want to go to high loops. You want to go to loops. So there's a conjecture, it's still a conjecture, where you can generalize this. Maybe let me just write it down for gravity. It's basically you need some loop integrals. The product of J equals 1 to L of dLj with d over 2 pi to the d. Okay, maybe there's a symmetry factor, some symmetry factor. And there's a sum over the, again, cubic diagrams. That sum is labeled I, and then ni tilde divided by these Feynman propagators. Okay. So that's a conjecture, and these are Yang-Mills numerators, and they satisfy this. The hard part of this is to find numerators that satisfy that at high loops. Right? You need to find a set of cubic diagrams such that you get the correct integrand, right, with satisfying that property, and if you satisfy that property, you get gravity. So the hard part of that conjecture isn't that this is true. If that's true, that's easy to prove. What's hard to find is these sets of numerators, and that can be a serious problem. For example, n equals 4 super Yang-Mills, our favorite theory, 5 loops. It's still unknown after all these years. There's other examples at 2 loops where you run into other types of troubles where you find you can solve that, but you get representations that aren't very good. They have very poor power counting. So this has been a big problem because you want to go on, and if you can't even write down the damn integrand, you get stuck. You can't even write it down. Well, then you can't go off and study things like ultraviolet properties of supergravity theories because you can't even get the integrand. Okay, so how do you solve that problem? Well, the key conjecture is that these numerators can be found or that they exist. They always exist. That's the conjecture. Yeah, but well, it would be a happy world if we were interested in one loop, but we're interested in 4, 5, 6, 7, right? So there, we're basically stuck unless there's a way, this way of generating something like this for generating gravity loop integrands. We're stuck. We're stuck on line 1. Yeah, these would be, this is the conjecture. Okay, so the problem is we're stuck, and we don't know how to do that. So and I guess in the spirit of the talk, every time you encounter a problem, you don't solve the problem. What you do is you go around the problem. So that's what we're going to do. We're going to go around this problem. Yeah. But yeah, that's correct. So here there's only cubic, but there we're going to have more graphs. But never mind, we just need to get an integrand. Any means necessary. Okay, and it turned out at 5 for n equals 8 supergravity at 5 loops, we did have a solution to the problem, which is basically by patching this. We had these like violations of this, and they determined certain contact terms. It was a long, complicated story. That solution, it worked. We want a better solution. Okay, and we want a solution that we can just apply very generally, that we know how to go about doing it. Okay. Oh, and there's one other problem related to this, which is we've been working on gravitational waves, and last time I checked, gravitational waves, at least what people are interested in, do not involve the dilaton. They are for Einstein gravity. And you can do a little counting, let's say in Yang-Mills, right? The number of helicity states is 2. So Yang-Mills squared has 2 times 2 states, which is not right. Let's look at gravity, graviton. That has two states, right? So we got the wrong theory. Now at tree level, everything is fine because the extra states decouple. It's not a big deal at tree level. When I said you get Einstein gravity, I wasn't lying. Loop level, it's not true, because these extra states, they don't decouple. They can certainly go around the loops. Those extra states are that's the dilaton, a scalar, and the antisymmetric tensor. So if you go to a gravitational wave theorist and you say double copy, we can do it, what about the dilaton? Got to get rid of the dilaton. And this construction here does not get rid of the dilaton. So you actually need to do it in a different way so that you can get rid of that dilaton without any trouble. Okay, how do you get rid of the dilaton? And there's a very simple answer. I just mean the theory, the double copy theory is not Einstein gravity. It's a theory with extra states, and those extra states are the antisymmetric tensor and dilaton. If we're interested in n equals 8 supergravity, no problem, because those states are in the spectrum. So there's no problem. But if we're interested in gravitational wave physics of black holes in our universe, not in some supersymmetric universe, then we got a problem. And the solution to that is not very complicated. What you do is you do cuts, right? What you do is you take a tree and you sew it, and right in the sewing, we say only gravitons can propagate because we have access to the states that are propagating. So we stop the dilaton by putting in a physical state projector that removes it. We do double copy here, we do double copy here. These are trees. These are trees. Okay? So we double copy, no problem. Remove the unwanted states by putting in a physical state projector, the normal way. Okay? But notice what I just said. I said, in the unitarity cuts, double copy is no trouble, right? Because we built, suppose we're interested, we're interested in trying to do 4-loop calculations for gravitational waves. So how do we do it? Well, let's draw. Maybe we do it like this. I'll just draw some cut. Okay, there's a black hole or a scalar. Okay, I'll put a tree here. There's a bunch of trees. There we go. Okay, so I want to do gravitational wave problem, right? Then the way I do it is I build unitarity cuts out of the trees. I have a spanning set so I can construct the entire integrand. I do double copy here, double copy. Everywhere, right? No problem. I have a dilaton, no problem. I remove it. Right? This is cut, this is cut. I remove the unphysical states, or the ones I don't want. I remove the dilaton from all these places. Right? So I can get double copy. I can remove dilaton, unwanted states, to any loop order simply by doing double copy at the cut level. So now you might say, well, gee, then why don't you do supergravity like that? Why don't you do it like this? And the reason is because in the past, to go from the cuts to the integrand was complicated because we didn't have a basis, right? Because the cuts were written in one set of labels, the integrand's written in another set. We don't have a notion of a basis. We don't know how to map terms one by one from the cuts to the basis, right? We can't do unitarity in the past we could not do unitarity easily because we didn't have a basis. Now we have a basis. So the solution of how you do double copy to all loop orders is trivial. What you do is you just do it in the cuts, right? So double copy all these trees, feed it into, write this in terms, this cut should be written in terms of the basis, and then we map it to the integrand. So let me explain a little bit more about that, how that works. Okay? So instead of talking about some for loop, let's go back to look at one loop. So let's do it one loop with those words, the words I just used. Okay. So the point number one is double copy is trivial, or no, maybe say trivial, straightforward, in any cut built from trees. Okay, so that means I can get a double copy expression for a cut. For example, this complicated cut. Then the next task I have is I need to take the cut and I need to bring it to an integrand. Maybe I should write the union of all the cuts, or the sufficient number of cuts to build the entire integrand. We call it a spanning set. The union of all the cuts has to be brought to the integrand. And the way we do that is we use the basis. Okay. So maybe to just explain what I mean by that, let's look at some integrand. Let's say in one loop, and let's suppose the integrand looks like this. So so this is these are the inverse propagators. Okay. And let's suppose I have, just for argument's sake, that diagram. There's my propagators, P1, P2, P3, P4. And just to be clear, let's say P1 is L square, P2 is L minus P1 square. This is 1, 2, 3, 4. Okay. Oops, this should be P. Sorry. Okay. Etc. Okay, and then up in the numerator, let's say I have, P1, P2 plus P2, P3. It just happens to be of this form. Okay. Okay. And now I consider a cut. Yeah, okay. Now I'll be done. Okay, now what I do is I consider a cut. So maybe I'll do this cut. Like this. Okay? And what this means, what this cut means, is these two legs, so these are the cut legs. I'm supposed to take P2 to 0, and I'm supposed to take P3 goes to 0. Okay? So then what I do is, up in the numerator, let me leave the denominator alone. I'm just going to leave that. up in the numerator, we see what the action of the cut is, right? It just crosses this out, and it crosses this out, but it keeps this term. All right, so what a cut is, and this, by the way, is true to all loop orders except maybe for some combinatoric factors. When you say the word cut, it's equivalent to saying, I am keeping a term in the integrand, right? See, the cut, it either keeps the term or it drops the term. And this is true to all loop orders, because the action of the cut is trivialized if you use the inverse propagator basis for these numerators. Okay? So in fact, let me make that equals instead of goes to. There's a one-to-one correspondence. If I look in a cut, I see the term in the integrand exactly as it appears in the integrand, but I have to be working in the basis. If I'm not in the basis, chaos rules. But in the basis, every term is unique. And if I go to the basis for the cut, and cut is a collection of diagrams, it's nothing but a collection of diagrams with certain numerator terms set to 0. I can leave the propagators alone, but numerators I set to 0. So the idea is that I can construct the integrand very straightforwardly. I look at a cut, I map to the basis, inverse propagator basis, I have the cut condition, I see a term, I declare that to be a term in the integrand. I mean, these cuts are generally, yeah. Yes, but they cut their, yeah. So in fact, no, a cut, so up to combinatoric factors, a cut is an integrand, except the labels are particular. But no, but the thing is, so I have the cut labels, and I have to map it to the basis labels. I have to treat this thing as if though it was an integrand. Okay, there's a little issue that I have to say something about the combinatoric factors. But if you ignore the combinatoric factor, just forget about combinatoric factors, this thing is literally a term in terms in the integrand. Except the labels are all messed up. So then I relabel it, and I relabel it into the basis. Once I'm in the basis, I pick one term at a time, and I compare. Okay, and the only thing I have to warn you about are combinatoric factors. So the first thing is, well, we can even do this at one loop. Suppose I'm looking at this cut. All right, I look at this cut. And this cut, in terms of the basis, let's again ignore combinatoric factors. It's a collection of diagrams. Right, it's a collection of diagrams, et cetera. Plus dot, dot, dot. And now I'm looking at another cut. I'm looking, let's say, at a cut in the other channel. This thing is also a collection of diagrams written in the basis. Now I'm in the basis. This is the basis. This is the basis. Okay? And then I'll find this. Let's see, there'll be bubbles like that, etc. Okay. And you may notice something. This one only appears in this cut. This one only appears in this cut, but this appears both times. So the rule is don't double count. If I fished out the term from here, don't count it from there. They have to match, of course. If they don't match, you made a mistake. So that's one example of combinatoric factors, that the same term can appear in multiple places. But okay, if you see it once, just don't count it again. Maybe use it to double check. And the other thing is sometimes in cuts, the combinatoric factors, here's a good example of two loops. There's one term. So this is one term in the integrand. I can take that one term, I can cut it this way. 1, 2, I'm almost done. See if I can make it on time. And I can cut it this way. So this is in the same cut, right? The cut is identical, but it appears twice. So the same term, one term in the integrand, there's the term in the integrand. No propagators are canceled. Let's just look at the term where no propagators are canceled. So it's one term, it has two cuts. The rule is don't count it twice, count it once, right? So you have to understand the combinatorics in order to do this. But that's a pretty minor problem because to do unitarity, you always have to understand the combinatorics. So that's where this comes from. The union of the cuts is equal to the integrand, and this is true to all loop orders. And that's how we solve the double copy problem to all loop orders. We do the double copy on the cuts, and then we build the integrand term by term using this mapping. And it turns out you anyway want to do the mapping because it simplifies the integration, because then terms don't appear splattered in multiple places. So it's something we would anyway want to do, is organize it this way. Okay, any more questions? Excuse me? Yeah, so we never found BCJ enumerators for that. Maybe a good example is there's at 6 loops, there's a non-BCJ numerator for n equals 4 super Yang mills. And that thing, as it stands, cannot be used at all. I mean, if you didn't know about this, because it's not in BCJ form, so you can't double copy it. But now you can double copy it following this algorithm. You have to take that thing, and you have to first take the cuts of it, and then the cuts of it you would then map to this basis, and then you would double copy that, and you'd reconstruct the integrand. So we now know how to do that, the double copy for that 6-loop integrand that now exists. I just picked a bunch of terms. I mean, normally there's a spray of many terms. I just picked a couple examples, just some example terms.